I'm going to be talking about this beast called the Rubin Observatory, but I'm not just going to start talking about it. I'm going to walk you through how we got to that idea. So the talk here is called Welcome to a New Era of Cosmic Discovery, because I think that's where we're heading over the next 10 years, and specifically over the next year or so. So I'm going to start with something much simpler, which is I'm going to ask the question, what is an astronomer? What does an astronomer do? And if you're like me and most of the world these days, the way you find things out is you go to Google and you query it. And because we can look at images faster than actually read, you just go to Google image search and look at a couple of images and you figure out what the answer is. Or another way I like to say this is because I'm too lazy to read, I go to Google Images. An astronomer is a person with a telescope who looks at the sky. And this is not actually very far off from how we used to do things for about 300 or 400 years or so. We would ask for time on big telescopes. These are usually at tops of tallest mountains. You'd get your couple of nights, get your couple of hours, you'd go to the big telescope, you would observe. Before photography was invented, you would literally observe through an eyepiece. Then photography came along, you could actually take a photo and you could bring it back home to your university. Then you can look at the image, literally now through an eyepiece, look at the photo, and that's how you did measurements. This is why graduate students were very important to have. And then after you do that, you get a sense for what is it that you were trying to research. That opens up a whole other slew of questions. You ask for time with that telescope again, and you repeat this cycle maybe 2 or 3 times a year at most. Things have changed since a little bit, a lot. What we increasingly do, rather than building telescopes like that, like the previous one that get used by one person at a time, we build telescopes like this one. This here is the Sloan Digital Sky Survey telescope that's in a place called Apache Point, New Mexico. And what it does is it can observe a fairly large swath of the sky at once. On the back end, you don't put a photographic plate anymore. You put a huge digital camera. Here's the digital camera that was on this telescope. It had 36 CCDs, 36 chips. And now suddenly you have a wide field telescope and a digital camera, and no matter how many grad students you have, there's no way for you to manually go in and analyze all those data. So now you have to use computers. And now you have to teach, not grads anymore, but you have to teach the computer how to go and recognize those objects, recognize where they are, recognize what they are, measure their properties, and then turn them into large databases that now tell you suddenly basically what's on the sky. That's the change that's been happening in astronomy over the last 20 years. Rather than focusing on one or a few objects, we can now build telescopes that control the sky and create huge databases of what's out there that not that one person can use, but anyone can use. So let me give you a sense of scale, give you a feel for the scale of the change. How many of you have seen this picture before? Almost everyone. How many of you have seen it on Star Trek? If you know the episode, there's one person. If you know the right episode of Star Trek Next Generation, there's pillars of creation on the bridge of the captain's looking at for some reason. This here is one of the most famous images from the Hubble Space Telescope. It's an active star-forming region, a nebula where newborn stars are being created. How many of you know how big this is in the sky? Few people do, not that many. It's roughly this big, relative to the size of the moon. So it's just a tiny little piece that we zoom in when we look at something like the Hubble. And then this telescope, the Sloan Digital Sky Survey telescope, how big is a single image that it takes? It's roughly that big. So that's the change in scale. It takes about 5 minutes to take a picture like this with SDSS. In 5 minutes, we get the information about all of this. We don't get the resolution of Hubble, but we get a lot more information because it's finite variant. And if you can do that in 5 minutes, what do? You just go and start tiling the sky. So that's what this telescope did for about a decade and built an image that looks like this. This here is not an image. It's a plot of over 1.2 billion observations of stars and galaxies. In this case, this is a plot of galaxies only. You can tell that it's not uniform. There's this wispy thing we call the cosmic web that indirectly points to our current theories of Big Bang and how the universe expanded and so on and so on. All of that is encoded in here. And this took about 10 years to build. This telescope took about 20 terabytes of raw imaging data to allow us to do something like this. So this is what astronomers increasingly do. We don't just go to telescopes and look at the sky. We build telescopes like this. We then build huge computing systems and build algorithms to go and identify what's on those images. Our day-to-day work today has as much in common with physics and astronomy of old as it does with statistics, with data science, with AI, with things that folks work on in places like Microsoft or Google or Facebook. And that is a dramatic shift in what astronomy is. And so let me just plug in one local institution that I happen to have been the director of for the last 5 years. This is why at University of Washington, we have institutes like Juric, Institute of Data Intensive Research in Astrophysics and Cosmology. Because for astronomy now, it's not sufficient to be a physicist who just happens to look up. You also have to be a bit of a software developer. You have to understand computer science. You have to understand what computer hardware can give you. You have to understand the statistics, the data science, and everything to make sense of these data. How well did SDSS do? I told you that this telescope made a difference. These are some of the results, just a small selection. When it was built, it discovered the I think 5 or 6, I can't remember, most distant quasars known. These are the most distant objects in the universe we've ever seen. It built the most detailed map of the Milky Way. It found the most dark matter-dominated galaxies ever. So imagine a small dwarf galaxy where there are only about a dozen stars. And this is not a guess. Literally, we found galaxies that have 12 or 13 stars. And they're swimming in a bowl of dark matter, of thousands of solar masses of dark matter. That was found with this telescope. And then a whole bunch of other things, all from a single telescope, from a single data set. And to give you a sense of how impactful that is, I went to a website that it's called ADS, Astrophysics, NASA Astrophysics Data System, that essentially tracks citations in astronomy. And looked for the number of papers that use long digital sky survey data. There are about 3,000, and the number of citations to those papers, there are about 230,000 citations. And just to give you a sense of scale and compare to something that you've heard about, here are the same numbers for the Hubble. So in terms of what this telescope delivered, in terms of the papers, the citations, it's comparable to something that every one of us, including your kids, know about, this Hubble Space Telescope that did wonderful things for astronomy through the last 30 years or so. So that shows you how this approach of let's not look at one object, let's try to take the entire sky, download it, put it in a database, can enable really good science across multiple subfields of astronomy. So once you find something that works, what do? You go and try to build the next bigger thing. And that big thing is the Rubin Observatory. So we got an idea, as soon as it was clear that SDSS will work. Oh, and by the way, I forgot to tell you to point out an important thing. That up there is the Long Digital Sky Survey telescope that I showed you. It's in New Mexico, Apache Point, lovely place. You should go and visit. But look around it. It's surrounded by forests. What does that mean? It rains over there. This is not a place where you actually want to put a telescope if you can afford it. The reason why it's there was, as Nathan said, even before Rubin, SDSS was the first kind of precursor that everybody thought was going to fail. This was a project that was known that will not work because you just cannot do this. So the only place we could put it was, well, where we could afford to put it. So now that it actually showed that it can do as well as something that we launched into orbit, now we can build the real thing. So that's going to be Rubin. The idea is now we build a telescope, not with a 2-meter mirror like SDSS, but with an 8-meter mirror. And your power goes as a square of the diameter. So it's much more than just a factor of 4. And instead of covering the sky once in over 10 years, we actually cover the sky 1,000 times over 10 years. And then we download that movie, we teach the computers how to recognize everything that's changing or moving, we put it in the database, and we enable all kinds of science, everything from discovering killer asteroids to understanding what dark energy is. And this is that observatory. After about 20 years in R&D, after about 10 years in R&D and 10 years in construction, it is finally almost finished. This is the Rubin Observatory. Can you see any trees? It's a really good site. It's probably the best site you can find for this sort of telescope. The telescope has, and I want to emphasize what Nathan said, it has deep roots here in this community in the Pacific Northwest. So it wouldn't have happened without Charles Simonyi and Bill Gates, who got it started. It was co-funded by University of Washington here, U of Arizona, NOAA and Research Corp. The current construction director is faculty at the University of Washington, and the reason why he's not here is that he drew the short straw, and he had to go to what's called the operations handover meeting in Chile, where they're figuring out how they're going to sign the paperwork to hand over the telescope from one person to the other next week. And this would not have happened without Nathan, who is really good at connecting people and apparently derailing careers. You walk into the observatory, this is what you find. It's an 8.4 meter telescope. It's really large, it's really impressive. If you ever get a chance to go there, if you want to go there, ask me. It's beautiful, you'll want to see it. It's really fast. So all of this important noise. How is the telescope spinning in real time? This is not a time lapse, this is the telescope. This is really you can barely see how small they are. This is 250 tons of glass and steel that can accelerate, rotate, and stop and take the next image in 18 seconds. The top, when it rotates, is faster than Usain Bolt, the fastest man on Earth. So do not try to outrun it. You will not win. This is the mirror. This was after it got out of the oven, the 8-meter oven under the University of Arizona football stadium, where they make these mirrors. Now it's up on the summit, and this beauty here is the camera. This camera has 3.2 gigapixels, 3,200 megapixels. If you wanted to display an image from this camera in its native resolution by using 65-inch 4K TVs, you would have to have a basketball court full of TVs to actually display the image. That's the scale that that's the scale of an image we take, and this camera takes another image of the universe every 30 seconds. Here it is just on the sides to give you a sense of the size of it. It's the size of a small jet engine. And I looked this up. I tried to find the closest jet engine, and the closest jet engine in size to this camera is Embraer 175 E2 regional jet. It's almost exactly the same dimension. So if you're ever going into one of these, just like take a look as you're boarding. That's the size of this camera. The camera's a lot more expensive than that. All right, so what does that allow us to do? It allows us now to build the fastest sky scanner in history. We've got a wide field of view with this camera. We've got a really fast telescope that can serve that wide field of view with photons. You add those together, now we can see objects in the universe to depths that before were not accessible to us with such width as well. And that allows us, it gives us the capacity to build the greatest map of the universe ever built. To essentially image everything from low Earth orbit all the way out to millions of years after the Big Bang. And again, let me give you a sense of scale. I talked about Sloan Digital Sky Survey. This image took 10 years to build, or this amount of data, imaging data, raw imaging data took 10 years to collect. For Rubin, the same amount of pixels we collect every night. The scales are the jump in scale is quite significant. So this here is the observatory, And if I gave you this talk a year ago, I would always have to talk about it in the future tense. But I don't have to anymore. Because we took our first data after, again, decades of development and data construction on April 15, 2025. We all sent in our tax returns and then went to the observatory. So the first image was taken April 15th, and then came about 2 most frustrating months of my life because we were not allowed to show it to anyone. Instead, we could show reaction videos. Like apparently these are popular on YouTube and TikTok and Ask Your Kids. This was their reaction after the first image got downloaded from the telescope. People were happy. It was a good day. Everything worked not as well as we expected. It worked better than we expected. So on June 23rd, 2025, we finally got the go-ahead to go and show these images. And there's a particularly interesting challenge here, which is I told you that just to show one image that this camera takes, we need to populate a basketball court full of HDTVs, which at this point our budget does not support anymore. That camera is really expensive. So instead what we did is we created a movie of the images that were taken that you can pan and scan and zoom in and zoom out, and that's what I'm going to show you next. So these are the first look images from the Rubin Observatory. This has been taken in the area of the sky in the constellation of Virgo. And what you're looking at is the Virgo supercluster of galaxies. There are about 1,500 galaxies in this cluster. They're about 50,000 light years away. Most of them are isolated. Many of them are interacting. I'm going to show you in a second a lot more detail. But this, to me, is the most impressive part. Everything that I just showed you is roughly 2.5 fields of view of Rubin. So we can do that. Take a snapshot, take a snapshot, take a snapshot, and that's it. It's really hard to talk about this telescope and to show you movies like this because they're just huge. The best way to experience it is to go to this website. It works really well on your cell phones as well. So if you go to skydata.app, click on it, and you're going to get a Google Maps type representation of these images, and you can zoom out to see the scale, and then zoom in to see just how deep you can go into the universe. So I'm going to pause here for 30 seconds and see people with phones. Oh, done. All right, skydata.app. That's where this takes you. Oops. All right, 3, 2, 1, go. So let me zoom in on one portion of that image and tell you a little bit why we all got so excited when we saw that this was. This here is a subset. It's as I mentioned, thousands nearby galaxies in the Virgo cluster, about 50 million light years away. The depth of this is about 26.5 magnitudes, and the astronomers in the audience are going to be really impressed, and everybody else should be impressed too. These are the depths that we used to associate with things like the Hubble Deep Field, these very deep images of the universe that we got with the Hubble originally. Let's take a look at what's in these images. The majority of what you see, these big objects are galaxies. But note these little dots as well. You might think that they're stars. They're not. They're actually galaxies as well. Because this telescope sees so deeply that even the tiniest dots in here are just galaxies that are really, really far away in the universe. I'm not sure if this one has a laser, but this blue bright dot in the center is a star. There are a few stars here, but virtually everything you see here is a galaxy because we see so deep that we basically run out of stars in the Milky Way and just see right through it. We see some very interesting galaxies. Look at the 4 up there. There are 4 galaxies that are colliding. They're stripping stars from each other. We didn't know until the 1970s that this could even happen. And now this is a beautiful example of of 4 of them doing this dance with this wispy material in between. That's not gas, those are stars. Those are tens of billions of stars that are being stripped from one galaxy from some of these 4 galaxies. Imagine if we lived there, our sky would look very different. Then we see clusters of galaxies. This whole thing is in the direction of the Virgo cluster, but behind that cluster of galaxies are more other clusters of galaxies. Here's a small cluster here. Note how all of these galaxies have roughly the same color. That's another cluster. But look at that circle up there in red. Those are also galaxies. It's also a cluster of galaxies, but note how much redder it is than this one. And the reason for that is it's further out. That's redshift. You've heard of redshift probably, if you talk to an astronomer, he's going to bring up redshift. That's redshift. They're literally turned red. You can see it. And then we have these 2 galaxies that are quite nearby that look almost like our Milky Way. And note the blue dots on top of these galaxies. Those blue dots are regions where new stars are formed. We can see those by eye. We're just looking for very blue things. That's that new band up there in the list of filters. So just based on this small portion of an image, I could teach introductory astronomy for probably about a whole semester. And that's the portion of the total image that I've just shown you. So this is a small zoom in. And this entire image, that's about 24 square degrees in the sky, is about 0.13% of the final footprint that we're going to cover in the entire sky. So this is just a small flavor. That gives you an idea of what we're going to have, what every astronomer is going to have at their fingertips starting next year. All right. These 2 galaxies, if this were CSI or something like that, I would just say hands, and we would zoom in onto one of the star-forming regions and see what's in there. Unfortunately, this is real life. So they're too far to do that. But we have regions like that where stars form in our Milky Way, so we can do that instead. So we went and took images at one of those places. And these are just beautiful. I'm not even going to narrate these. Oh no. There are millions, tens of millions of stars in the background, but in the foreground are 2 nebulae. One is called Trifid, one is called Rubin, that are being lit up by stars that have formed there. And depending on how hot it is, or how hot the stars are, they're shining either in red or blue, depending on which species are getting excited. And this entire image is roughly one field of Rubin. You can see these dust nebulae. That's where dust is. That's where a lot of the material comes from which our planets form in the end. And we're going to cover the entire Milky Way and take images of all places that look like this. And that's going to be, again, on everybody's fingertips starting again this year. All right, these are spectacular, but they're still just stills from a movie. I told you that this telescope can take not just 1 photo, but take many photos. And we tested that as well. Rubin can observe changes in the universe. So here's an example of one. This here is that same field called Virgo, but now we're looking at some objects where the computer told us that they're changing. This here is a variable star. At 2:43 it looked like that. At 3:15 it was 30% brighter. Here's one. Move to a different position. Here's another one. Fainter, about 10% brighter. And then we find another one. And you started to see the pattern here. It's not just 3 of them. It's more like hundreds. And the reason why these are interesting is these stars are what are called RI stars. If you find them, if you measure how quickly they change brightness, you know how far they are. If you've ever seen 3-dimensional maps of the universe, this is one of the ways how we find that 3rd dimension. So with Rubin, we can do this over more than half of the sky, build 3D maps, understand what a galaxy looks like. And for our final trick, objects in the sky don't just twinkle, some of them also move. And we detected those as well. So here's a star, here's a galaxy. And this thing that looks like a star is not a star. That's an asteroid. Look how it moves. This asteroid has never been seen before, it's newly discovered. We found not 9, not 36. But in the first night, we found about 1,000 new ones. Each of these dots is an actual position of an asteroid floating through this image. They're too small because the projector resolution is not big enough to actually show them to you. By the time we were done with this, just this test field, we found about 2,100 asteroids. And the nice thing with asteroids is you can also figure out their distance. So we can now zoom out and see where they are in the solar system. That's Earth, that's the Sun, and that's this one direction that we look towards where we're going to 2,000. And so in a few nights, we found 2,100 asteroids. And again, is that a lot or is that not a lot? Let's compare it to something that we can understand. Let's look at before Rubin, how much would the whole world typically find? So we found about 2,000. The whole world typically finds 20,000 every year. So in one night, we can get to about 10% of a typical yearly yield. So because of this is just one example, but this is an example of why, for example, Rubin will be a game changer in mapping the solar system, because it's just so much bigger, so much faster than anything else. We can go and discover millions of these objects. Okay, so let me give you, for my last 5 minutes, Rubin, I said, can discover everything from dark energy to killer asteroids. I thought the killer asteroids might be more interesting to talk about. So I'm going to just focus on the solar system and to give you a sense of what's coming over the next year or so. So here's a simulation made by one of our students, Jay Kurlander, here at the University of Washington, of the discoveries as a function of time once Rubin begins. So the number of new asteroids discovered after Rubin starts. And on your right-hand side, is it right? The other right. On your left-hand side, you see the solar system viewed from the top. The blue dot that you see there is the Earth going around the Sun. The Sun is in the center, we don't plot it. And all of these dots are asteroids that Rubin discovers. Let me restart this plot, this movie again. Look how fast it happens. Boom. In about a month, we already have hundreds of thousands of discoveries. In half a year, we get up to 1.2 million. And in about a year, we get up to 1.6, 1.7. And to scale that again to something that's relevant, first asteroid was discovered in about 1800. Since 1800s till today, the entire observational system found 1.5 million. In the next year, we're going to double that. And then in the next 10 years, we're going to further triple that. So that's the kind of power that you get now with these big telescope systems coupled to big data systems that can find all these objects. And I got curious why, and it turns out the reason is car insurance. There's so much fraud apparently with car insurance that if you have a dash cam to actually plot, to actually take a photo of the accident that may or may not have happened, you get a discount. So that's how that helped planetary astronomy as well. We know only about 40% of such objects that can potentially impact the Earth. And with Rubin, we're going to get that number, we're going to at least double that number to about 80% or so. Let's move further out in the solar system. One of the questions that we have is, where did the water come from in the solar system? Our Earth has a lot of water right now, but it didn't at the beginning. All of it evaporated when it was much hotter. The standard answer is, well, it came from comets. Turns out when you do the math, that doesn't quite work out. The answer probably really is it came from asteroids as well. And with Rubin, we can figure out where the volatiles are, where the water is on asteroids, how much of it is there. Were they sufficient to bring it all to the Earth? And also, can we go and mine it? The other thing we can do is we're going to find targets for space missions. Here's a space mission called Lucy that's going to near Jupiter to study some of the oldest asteroids in the solar system to figure out what the solar system looked like when planets were forming. Lucy already has its primary targets. With Rubin, we're going to probably double the number of places that it can go and visit. And then when you go farther out into the outer solar system, you reach a place called the Kuiper Belt. And the most well-known inhabitant of the Kuiper Belt is Pluto. Who remembers that Pluto used to be a planet? Everyone, all right, me included. Now I'm going to make you all depressed because I gave a similar talk to our students, all of whom at this point have been born after Pluto stopped being a planet. So to them, this is like, yeah, it's not a planet. What are you talking about? We love Pluto. Other than that little controversy, the reason why that area of space is important is it tells us a lot about what happened early in the solar system. It turns out it can tell us that the planets didn't start where they are right now. We think of the solar system as something very unchanging, as something that's been around for billions of years. Well, that's not true. The planets, when they started, were much closer to the sun. They were much closer together. Neptune was about half as far away from the sun as it is right now. And then something happened. We don't know what that something is, but it expanded our entire solar system out by a factor of 2. And possibly even changed the order of some planets. If you look, this panel over here, this teal circle is on the outside and the blue one is on the inside, whereas at the final panel, the teal is on the outside and the blue one, the blue is on the outside. Trust me, it's there, I can see it. And the teal is on the inside. Pluto and Neptune may have changed places. This is currently a theory. We don't have enough data to exactly know what happened, but with Rubin, we're going to be able to map out this process in a lot more detail. One of the things that could have happened early on was that we had more than just 8 big planets. We may have had a 9th planet that may have gotten ejected into interstellar space, never to be seen again, or it may still be sticking around. There are some interesting indications in the orbits of those Kuiper Belt objects that they all seem to be pointing in one same direction. That doesn't happen naturally in nature. If you have something ordered in nature, somebody had to work to bring that order in. The default in nature is chaos. Somebody here might be that 9th planet. There might be a 9th planet in the outer solar system that we still don't know about, and I'm talking sizable planets, something the size of Uranus or Neptune, that may be ordering all of these Kuiper Belt objects. If it's out there, we're going to find it with Rubin. It's exactly in the right range of brightness for the telescope to see. It's exactly at locations where the telescope is going to look. We either find it, or we're going to be able to say that it doesn't exist, or if we don't see it, there are a couple places in the sky where it's really hard to see things because it's very crowded. We're going to be able to point others to go look there. And then to finish this off, we're not the only planetary system in the universe. There are hundreds and thousands and billions and billions of others. Here are just some of the planets that were found orbiting outer stars. We cannot go and see them directly or sample their planetary systems directly, but they sometimes kick out asteroids and comets from their planetary systems and send them our way. And those we can see. They're called interstellar objects. Here are 2 examples. One is the first one ever found. It's called Oumuamua. The other one is called Borisov. They were discovered in 2017 and 2019. And then the third one was discovered just as we were starting to test the telescope. And this July. And if we were started testing the telescope maybe a month earlier, we would have been the ones who found this object. Instead, it was our friends at Atlas Project at the University of Hawaii. But we did take an image of it with Rubin, and here you can see how bright it is in Rubin. For us, this is a super simple thing to observe. And I'm happy to say that this kind of work is already being supported by you, by Hertz Foundation. One of your fellows, Aster, over there, just gave a phenomenal talk at the university on campus earlier today about comets in the solar system, interstellar objects, and dark comets. And those, Rubin is going to be game-changing for figuring out where those come from and what's really out there. So to finish this, where we're going is the next decade with Rubin Observatory will really be about mapping the universe, and we're going to collect so much new data, so much data. Whenever you increase the amount of data you have by a factor of 10, you discover new things, you change paradigms. We're going to be rewriting textbooks. And all I had the time to do here was tell you a little bit about that in the context of the solar system. But the same is going to be happening in the context of galaxies, in the context of what's called time-domain astronomy. We're going to be discovering the rarest phenomena in the universe. Imagine a star passing by, let's say, a black hole, and then black hole shredding it apart. We're going to be seeing dozens of those. And finally, some fundamental questions about our universe as a whole. What is dark energy? What is dark matter? So with that, I'm going to stop. I hope I've given you some flavor. We're going to chat a little bit, Scott and I, about what is it that Rubin can do, and please ask us questions as well. But the message here is we're on the precipice of a new avalanche or tidal wave, or choose your metaphor, of data coming into astronomy over the next decade. We really are getting ready for a decade of discovery. So thank you all.
So the first thing I want to start off with is a lot of people in the audience, and me, and definitely you, we're scientists. And in the tree of science, we all have very intricate, little detailed specialties. You gave a beautiful overview of what Rubin is going to do. And I was wondering, personally, what are you most excited to see that's going to come out of Rubin in the early days?
I think in the early days, these opportunities in the solar system that I showed you, I think they are going to be they're just remarkable. Think about it. Over the next year or two, we have a chance for the first time in 150 years to discover a new planet in the solar system. We have a chance to understand how our solar system formed to be the way it is. We might discover an asteroid that's hurtling towards us that we're going to go and then deflect. And the exciting thing to me there is, both scientifically, it will answer some of the big questions that we've had for decades in this field. But also, Rubin is a 10-year project, and everything I just told you happens over the next 12 months. So it'll be, the solar system will be remarkable as kind of an early, a demonstration of early science that can come out of like this next 1 to 3 years are going to be phenomenal.
Thanks. So with the Hertz Foundation, one of the great things that it does is it helps students, right? It completely changed my life, and I'm extremely appreciative for the foundation of that. So for graduate students, I mean, as you mentioned even in your talk, graduate students, they drive science. They're one of the ones that are some of the people who are doing the most work. And it's changed. Astronomy has changed. You mentioned the way that we used to do observations and look at individual objects and stuff, and we're moving to the survey-based way of doing things. So I was wondering what you thought about how is it changing the way that we train students? How does it change the way we select students? What are we looking for to do this kind of work now?
Yeah, so our students, I think what the Hertz is doing, and what I've heard about how you select the fellows is basically how we're now looking for graduate students. They have to be broad, they have to be creative, and they have to be ready to jump on opportunities. Because one of the interesting things with this type of science, with survey science, is you can do what you've always done, which is, you have your particular object of interest that you study, and now you don't have to go to the telescope, you can instead create a database for that object of interest and so on, and that's going to continue working. But an interesting, different way of approaching this is, suddenly you have the entire sky in front of you. And you may be working on some project and then notice an opportunity while you're doing that in some maybe completely different area. And you realize, oh, I know how to do that. And we want the students now to be kind of both ready and comfortable to make that jump when they notice opportunities, things that maybe no one has imagined that can be done with this data set, that first they're able to notice that something like that happens, so that they're broad enough that they're not just a solar system person, quote unquote, or a dark energy person, but they have very broad areas of interest. They understand the data set, they understand technology, And even if they're working on solar system, when they realize, oh, there's something really interesting that I can answer for extragalactic astronomy, that they're fearless about jumping and trying to do something like that. A large amount of science done with SDSS was not exactly that way, where, I was a graduate student back then, so I was really lucky to be born at just the right time to come in and take advantage of everything all those good people who built SDSS built for decades before me. So that's why I feel I have to repay that by now building the next telescope. Yes. And I started working on asteroids, interestingly enough, on SDSS. And as I was doing that, I realized, oh, you know what? The largest ever survey of stars in the galaxy was 70,000 stars. And I just happened to be sitting on 50 million. Guess what? I'm going to go and build a three-dimensional map of the Milky Way. And those are the kinds of things that we want to encourage our students now, like to notice those opportunities to jump on them. Right? It's not the sort of thing anymore where you enter your career and what you study for a PhD you go and do for the next 20 years. Now you have to be ready to pivot when an opportunity arises. Sorry, very long answer.
Oh, no, yeah, I think that's completely true. And I'll do two direct follow-up questions to that, but then I think we'll go and see if we have some questions from the audience. So one of the follow-up questions is, you said that we want the students and the people who are using these big survey data sets to notice things, right? That's kind of the goal of surveys, is to find things, right? So my question is, with this massive amount of data where we're having to develop brand new techniques to go through the databases and stuff, many of them, because there's so much, we have to separate the wheat from the chaff. Many of the algorithms that we're using in these fields are quite like mashed filters, where we know we're looking for asteroids, or we're looking for high redshift galaxies, or we're looking for wobbling stars that might have big planets in them, or whatever your object is. You design an algorithm to find exactly that object. So my question is, how do we handle to find the other stuff, the unknown unknowns, in massive data sets like this?
Yeah, that's the $64 million question. The kind of, this day and age, the typical answer is, well, we'll use AI. I think that is part of the answer. There's a different answer, which is, it's a question of when to apply an increasingly complex technique. With Rubin, the data set is going to be just so large that early on, if you want to go and look for rare objects and you have a sense for what is it that you're looking for, even a quite silly two-dimensional plot, x versus y, that before would yield 0 objects, will now yield hundreds, just because there's so much data. And what I tell to my students is, if we're looking for something interesting, let's find the dumbest, simplest method that will get us that. Because these first couple of years are going to be a race. Now, when we exhaust that, as we're going through that, we're going to go start looking for, as you said, unknown unknowns, things that are harder to find and so on. And there we're definitely going to want to apply supervised classification, unsupervised classification, clustering. We want to find clusters of objects that all look alike, but don't look like other objects. So we have this joke at the department that we want to do a project named WACOs. That stands for Washington Catalog of Curious Objects, where we're going to do exactly that. Like, let's find all the things that look alike, and maybe the first 50 things in that list are going to be known variables, known types of planets, known this, known that. Then we get to type 51, which no one's ever seen. And then we try to figure out what that is. And another interesting way of doing this might be, go back to AI. If you look through the scientific literature, astronomers and physicists, especially theoretical ones, I'm a theorist by training, so I can make jokes about theorists, are very creative. They will sometimes come up with ideas on what to look for 50 years before it's even possible to look for. And those ideas will be written up in papers, and unfortunately usually forgotten. I bet you that there are now papers somewhere in journals from 1970s that predict some really curious, really rare objects that no one's ever thought we're going to have enough data, but now suddenly we might find dozens of them. So what would be really fun to do is to go train AI on all those papers to essentially learn the properties of all these predicted objects that no single astronomer can remember, and then crawl through our databases and look for things that match that. So that would be, I think, a really fun project that is not obviously doomed to fail.
So that leads into my second follow-up question about what we train our graduate students to look for. So you mentioned, and I do the exact same thing with my students as well, you try to skim the cream on whatever project you have first. You know, you get 90% of the results with 10% of the effort, kind of thing. So when you're doing that with a survey like this, you're going to generate a whole bunch of stuff. If you're looking for asteroids or whatever, you're going to find a ton of these things. But then one of the first things you do when you have that first sample is you look for the stuff that's at the extreme. You look for the things which are slightly different or weirder than you've seen. And then you investigate those things in depth. And so that's where this question's about. If we want to go in depth, so Rubin's going to do fantastic things giving this collection, but it's not the only game in town. We need other things. And so I want you to comment a little bit, if you can, on the system of telescopes, multi-wavelength observations. How do astronomers deal with those things that they need to look at individually to find out more?
Yeah, so another way of, or a related question to that is, you know, is Rubin, the question I often get is Rubin better than James Webb? And then I have to say, no, that's comparing apples and oranges. Rubin is designed to image the entire sky and give us kind of statistical sense of what's going on, find the most interesting objects, and then you use telescopes like the Webb or like the Keck telescopes, other big telescopes, to go and zoom in and find individual objects. So we're like, there's over the next decade or so, there's going to be this dance where Rubin finds the most interesting thing, and then it gets followed up by other telescopes. Now, the other thing, the wrinkle to that is some objects we want to follow up really, really quickly. There are like explosions of stars that you just caught them in the act of happening. And when you see a thing like that in Rubin, sometimes within minutes or hours, you want to be on that star with a large telescope, with a spectrograph, a different kind of instrument to go in and get the details. So one of the things we have in Rubin is something called the alert stream. Every time we take an image of the sky, within 60 seconds, we compare that image to the previous time we went and visited that part of the sky. Anything that's changed, we send out an alert. So you can be anywhere in the world, you'll be getting those alerts. And if you notice something that piques your interest in one way or another, you can go and follow it up with your telescope.
Let me just jump in real quick. How many alerts are there going to be per night?
About 10 million per night. And that's the problem, right? So there are two parts of the problem. One is about the 10 million alerts per night, 9,999,000 of those alerts are going to be deeply uninteresting. It's the 100 or the 10 or the 1 that you care about. How do we filter those out? That's question number one. That's an algorithmic question. What data do I need to bring together and fuse to identify those? And the second question is, all right, now identify the most interesting object in the universe for today. Which telescope do I use to go follow it up? And this is where I think we have a bit of a problem, especially in the US, because we don't have that many facilities that are powerful enough to go follow up Rubin discoveries. And we started, talking about 30-meter telescopes. Typically, a survey telescope is maybe 10 meters, and you want something that's a factor of 3 larger, so let's say 30-meter telescope, to go and look in depth to get spectral functions. We started talking about those at roughly the same time we started talking about Rubin. Rubin happened, but the 30-meter telescopes kind of got stuck in development. So ironically, we in the US now may have the biggest survey telescope there is, but it might be the Europeans who do all the follow-up, because they've been working hard on building their 40-meter telescope. So that's a thing where I think we need just worldwide, in the US as well, but worldwide, bring more large telescopes online so we can follow up all the Rubin service.
Yeah, and just to add, as someone who does most of my observations in the radio, X-rays, and gamma rays, it's not just optical telescopes. These Rubin's going to find objects that we need to use, for instance, X-ray observatories, which are in space right now, which are in danger of being defunded literally right now. The Chandra X-ray Observatory, for instance, might be defunded now, depending on what the government decides when it comes back online. Or radio telescopes. The world's building massive, massive radio telescopes to do radio surveys of similar type things to what Rubin is doing. These things work as a system together, and astronomers use all of these things together to figure out what's going on in the world. It's a really, real crucial thing for us to get the most science out of these objects. All right, are there any questions in the audience? I'm kind of blinded, but I saw your hand go first.
Yes, I have a general idea that you can see the effects of dark matter, and you can see what you think are the effects of dark energy, but is there some way that you think you can get some insight into what dark matter is and what dark energy is?
We hope. So, both of those problems are tough ones. Right? For dark matter, we systematically over the last, what has it been now? First suggestion was speaking, what, the 30s? So it's been almost 100 years now of dark matter. For dark matter, we systematically started excluding things, what it cannot be. You know, is it planets floating out of the universe? No. Is it black holes of a certain size floating out of the universe? No. Et cetera, et cetera, et cetera, et cetera. And we got to a point where the majority of people are convinced that it's particles. It's elementary particles that we just can't detect for some reason. And there was a lot of hope that we have a theory of what these particles could be. It's supersymmetry. We're going to build a Large Hadron Collider at CERN. LHC is going to go find one of these things with the Higgs boson, and after that, supersymmetric particles, and we're all going to be happy, and it'll be the end of physics. And I can retire. That didn't quite work out that way. LHC did find Higgs, perfect, but no supersymmetry was found. So that's still a big question. What is dark matter? And people are now bringing back all the kind of more speculative theories because we really can't exclude them anymore. But like to be frank, we don't know what dark matter is, and it's everything we have right now is consistent with it being some kind of a particle. Dark energy, on the other hand, is even more mysterious. The best prediction right now, well, not prediction, description of what it is that it's a property of space itself. There are alternative theories, numerous alternative theories, that do have observational consequences. They predict that the universe should expand in one way, if this is true, another way, this is true, another way, this is true. And that is what we hope to find out in Rubin. Rubin is what in the business, quote unquote, we call a stage 4 dark matter experiment. It's a factor of 10 more powerful than the previous ones. It's going to measure two constants called W and W dot, essentially how the universe expands and how its expansion changes. And depending on what dark matter might be, different theories predict different curves for that evolution. What we're desperately hoping is that we're going to find out that the curves that we measure do not match the dark energy as the property of space theory that's currently the favorite one. Because in some ways, if dark energy is a property of space, it gets us into a blind spot because we don't really know what this next experiment to do that. If it comes back and says dark matter is this really weird particle, or there's something that's consistent with a prediction of there being another universe on an adjacent brane and somehow they're communicating, we have the next thing to do. So there's this entire community of particle physicists now who are rooting against Einstein, hoping that this cosmological constant is not the answer. But we should come back in maybe 5 or 6 years. It'll take a little bit more time to accumulate data for dark energy and see what we measured. That is the big hope for Rubin, that we will find something that tells us the nature of dark energy, not just a description of it.
Yeah, back to
There's one in the back, and then maybe on the left side of the room next.
So, did I hear you earlier mention that you had some interesting data or observations that you were somehow restrained from sharing with the general public?
Oh no, we had about a 2-month embargo period between the first image and we were allowed to start showing them. And it just, when you build a $1 billion project, and when you first show it to the public, you want to show it in a way that's going to be understandable and that that will explain to the public, why is it that that they paid $1 billion for this. So that's the time that you need to build that up. That's why there was a delay. There's nothing. I promise there was nothing nefarious about it. You don't pay me enough to keep secrets.
Just as a quick follow-up to that though, when Rubin was in development, when the certain agencies that have 3-letter acronyms realized how powerful Rubin would be, seeing things that go around the Earth, for instance, there were some issues. Can you maybe describe and tap into that?
I would. Well, let me tell you about a survey called Pan-STARRS that I worked on as a postdoc. This was one of the things that we did in between SDSS and Rubin. It was in Hawaii, phenomenal survey. Fortunately, it was co-funded by the Air Force, and unfortunately, it was co-funded by the Air Force. And the Air Force realized, oh, this thing is great for astronomy, they're gonna go test their cameras, but they might also reveal where our satellites are. So the Air Force found a solution, which is they told us, you're gonna run this piece of software that Boeing developed. And that piece of software is going to identify anything that looks like a line in the image, because if a satellite goes by, it looks like a line. And it's going to just cut out those pixels. You're never going to see it. Nobody's ever going to see it. And we had to say yes, because, money. And the problem, though, was that the camera that we're testing for the Air Force had interesting electronics issues that caused the linear features to show up in the signal, which the software happily identified as potential satellite streaks. So we would get an image where about a quarter to a third of it was missing. And not like just cut out a third, but this stripe is missing, this stripe is missing, this stripe is missing, this is missing, and now I have like a little triangle of data here, a little triangle of data there, a little triangle of data there. So that was my first foray into the kinds of problems you can get into when looking into the sky with powerful telescopes. Now, the reason why I'm telling this story is because we got really worried that we might have the same issue with Rubin. Fortunately, the Pan-STARRS experience allowed the Air Force to actually check, how many satellites might get discovered by these telescopes, and somebody downloaded data and discovering them. And they concluded that the number is approximately 0. So 3 years later, they've given up on the sensory, and for Rubin, they didn't try. For Rubin, instead, what they said was, we're still worried that somebody's going to see these objects, but there's a time scale after which we stop being worried. And this is, if somebody here works in the national security community, they may understand where it comes from, but I'm not going to speculate. But apparently, after 80 hours, we can share anything. So the only restriction we have on Rubin is raw images. We cannot give out raw images to everyone for 80 hours after they've been taken. For what's called the alert stream, anything that we can positively identify as being a star galaxy or something that's in outer space, not moving really fast, we can send it out immediately. But we cannot give you a full image until this 80-hour embargo expires. I think this is also caution. It may go away after a few years, but it's significantly better than your beautiful 3.2 gigapixel basketball court image getting chopped up into pieces like the toddler went with scissors through.
So I guess my question is, as a scientist, did you ever feel that your source of funding interfered with what you would want to have done with sharing your information?
So I hope no one's recording this. The short answer is yes, but not in a way that is nefarious. We're scientists and we care about doing science, but the folks who fund us have to care about other things as well, right? Like imagine I'm going to make up an example on the spot, which probably be terribly wrong, but imagine I'm in biotech, and imagine I find a way to cook up all these interesting things in the lab that potentially, if they escape the lab, might cause some issues. There should be someone looking over my shoulder. Sometimes we get very excited about things and want to go and just do it. In astronomy, that's less of an issue. Except when you have these kinds of things, like we build really massive telescopes that can go and accidentally reveal other things that we astronomers don't know about, but others do. And when something like that happens, I think it's incumbent on us to try to understand the concern coming from the other side, because these people they're not evil, they're not anti-science, they have their concerns that they're trying to solve, just like we have our concerns to try to solve. Understand where they're coming from, understand how we explain to them what it is that we're doing and how it may or may not affect what it is that they're worried about, and vice versa. Usually when you approach it that way, it tends to work out. That's how we did it with Rubin. There were lots of discussions, and then we came up with this compromise solution that addressed their issues and enabled us to extract 99.999% of the science. So I'm kind of more, I don't know, I tend to approach these things in good faith, because I think if somebody's telling me not to do something for some reason, I'd like to understand that reason, and we can discuss and find a way to proceed in a way that both of us can be happy with.
There was a question back there, yeah.
Yeah, I apologize, it's another politics of science question, but hopefully maybe a little easier. So when you're describing, you talked both about tiling the sky multiple times over, but then also looking at specific things. And the way I interpreted it was that those are different. That you're by looking at something, it's not just like looking into the space of the tiling. If that's true, how are those prioritized, and how do you determine when to dive into a specific point and look at it as compared to continuing to tile more and more?
So this telescope just goes and tiles the sky. It never goes back to look at a particular point. What we do is we alert the worldwide community on this 10 million per night problem, 10 million different alerts on what might be interesting things to look at. And then different people with different programs and different telescopes will prioritize things differently depending on the science they want to do. Typically the way it works in astronomy is if your university has bought into a telescope or paid to build your own telescope, then you get to do whatever you want with it. If it's a national telescope, you typically put in a proposal for a certain kind of science that gets peer reviewed, and then you may get, let's say, 20 hours in a quarter on that telescope. And you say, I'm going to use those 20 hours to trigger on objects that look like this in the Rubin data stream. So that's how I think that's how it will be done. The interesting question becomes of global optimization. What happens if 10 people have the same idea, and you got 10 telescopes that are all chasing the same object, and then you get into nice, interesting game theoretical problems of how do you optimize that while making sure that everyone kind of gets some credit for what is it that they're doing. People are thinking about that, but I think that's probably going to just emerge through after the first year of the survey or so, as people try to both collaborate and compete and figure out what works.
Okay, right here.
Yeah, so Scott mentioned some of the telescopes which are not ground-based. And do you visualize another Rubin which would be based in orbit that would have broader spectral capabilities? And what would be the advantage of that? What do you think?
I think that's I think that's phenomenally interesting. And to broaden that a bit, the access to space is becoming much cheaper now, factors of 10 to 100 over the next couple of years. So that makes it possible now for us to rethink how we build space telescopes. The reason why space telescopes are so expensive, one of the reasons, is because they must not fail, because partly the launch cost is very expensive. So the equipment that you put on top of that controlled explosion better work once you get it into orbit. Now, if your launch cost goes down by a factor of 10 or 100, you can afford to say, I'm just going to cook something up, like a rough 4-meter mirror in my university lab. We're going to put some camera on it and so on. And if it explodes, I'm just going to build another one. And that opens up possibilities for all kinds of interesting experiments in space. So I think the next thing that we build, especially if Starship works out, 10 years from now, we're going to have all kinds of interesting astro projects in space, and not necessarily run at the national level, but at like individual universities figuring out some very interesting things they're going to put out. I don't think that a wide field, like big 8-meter telescope or Rubin is going to be the next thing. I think first we're going to start with smaller experimental things now that any university group on a small grant can start launching things into space. But I think that's the next frontier. Like I'm starting to think what to do after Rubin, and then thinking like astronomy in space is going to be really, really big starting maybe 5 to 10 years.
What do you think you can see that will be different than what you can see?
Oh, you can go in infrared. Infrared is what we cannot see it here. Infrared gets you farther out in space. So you start seeing more distant galaxies, things closer to the Big Bang, like trying to figure out what those early times were like. How did galaxies form? How did big black holes form? All of these things that we don't quite understand about.
And so another thing you can do in space, which you can't do on the ground, is ultraviolet, for instance. And ultraviolet tells you about the youngest stars. It tells you about black holes. It tells you about neutron stars. It tells you about active galactic nuclei in the local universe, which then teaches us about them in the far universe. There's also radio. There's a whole bunch of other stuff. So there is this bias. We all have our little blinders on, and we like to, the observers give the theorists crap, the theorists give the observers crap, the radio guys give the optical guys crap. Anyways.
But we all agree that we would love for someone to launch our stuff into space.
Absolutely, yeah. For much cheaper.
Yeah.
And actually, is there a question right there? Sure.
Oh yeah, so I'm curious what you think is the role of AI, in particular AGI, in the future of sort of how we do astronomy. Like, are you envisioning there's a world in which, you know, an AI astronomer agent is like interconnected to all of these sort of imaging systems, including radio and, you know, UV and other systems, and constantly running through like hypotheses, or is that like, where do you see is that future?
I think the honest answer is that we don't know how that's going to play out. I think the timescale of change in that area is over a few years, so like it's exponential. I can't predict what's going to happen like 3 or 4 evolving times away. I can't predict what's going to happen in 1 or 2. So I think we're going to do, for the next couple of years, we're going to do what everybody does. We're going to use AI agents in the way you just described. We're going to use them as assistants, helping us read papers, identify plausible theories. We're already using them as, let's say, software developer assistants. I don't want to call them software developers yet. But how this whole field looks like 5 or 6 years ago will really depend on how AI evolves over that time. If things stagnate, they might just remain assistants the way they are today. If things continue exponentially and we get something like AGI, where the AI comes in and just totally surprises me with something like out of the blue, where I have to go home and read 3 books to understand what is it that it's proposing to do, well, I think then we're going to be in really interesting territory. But I don't know where this is going.
I'd like to know what the Hertz Foundation is going to do if AGI comes online. Do we have any other final questions? We're almost out of time. Maybe a quick one.
I was wondering if you could talk about data management in this setup, because it seems like you're generating an insane amount of data. And has that actually been a challenge? Is this something that astronomy has figured out and it's not that big of a deal?
So I used to run data management for the telescope. So my experience here is very much from the software side. And I started back in like 2010, 2011. This was a very challenging big data problem because we're collecting about 6 petabytes of raw data per year. As you process it, that expands roughly by a factor of 10, so it's about 60 petabytes that you have to manage. And we needed we projected we needed about 3 or 4 petaflops of compute power to do it. In 2010, that sounded really scary. Today, like, when I talk to my friends at Amazon, like, they yawn. Today it's much easier. I think we can. We know we can do it because we're doing it. It's not that much of a challenge anymore. It still is a lot of data to move around and a lot of computing to have. But now we're firmly in the territory where on the data management side we're not breaking new ground. And if you're building a science project. I forgot who said this, but they said, you want 1 miracle for your science projects. Not 2, not 3, not 0, 1. And our miracle is likely the camera, because a lot went into developing the technology for that camera, and I'm really happy that my miracle kind of went away, because the miracle I was supposed to deliver was to process all these data. But now you can just buy it off the shelf. So I think we're lucky in that respect, that technology just...
I'm going to jump in though, and once again, yeah, I need miracles. Because the next generation, the radio telescopes we're building right now, for the next generation, you may have heard of the Square Kilometer Array, or here in the US, it's going to be the telescope called the DSA 2000. We're talking 10 to 100 times the data rate of Rubin. And that's going to start in the next 2 to 3 years. So he was really afraid in 2010. I'm really afraid right now. And astronomers are never satisfied with their data, so we always want more. With that, I think we're out of time. Thank you so much. What's that?
We've got a couple more questions here.
Oh, I thought we were out of time.
No, we're not out of time.
Okay.
Guys, here, Mike over here.
Sure. I have a couple of questions about near-Earth objects. So for one, how close to 1 AU of some major axis can you actually discover asteroids? Second follow-on question to that is, how much will you collaborate with space missions like NEOSurveyor? And then bringing it closer to Earth as well, are you seeing any Earth-orbiting satellites impacting some of the observations? You mentioned some of the Air Force ones, but constellations going up tens of thousands, even just really small objects as well that are very bright in Earth's orbit. I guess, can you speak to each level of that?
All right. So
closely?
how close then can we see near-Earth objects? We can detect objects all the way into the orbit of Venus. So we can see intravenous. Intravenous orbit objects. Because we observe it at twilight, at dawn as well, so pretty close to the sun. So that's when we catch those. Your second question was relationships to missions like NEOSurveyor. We're complementary. We both, as soon as we discover an asteroid, both us and NEOSurveyor, we report it to the Minor Planet Center. The Minor Planet Center integrates all those data and produces the overall catalog of what's out there in the solar system. We're going to hit the sky a bit earlier than NEOSurveyor, so maybe a year or 2 years earlier. So that will give us a little bit of an advantage, and we're likely to find most objects that NEOSurveyor would otherwise found. But we observe in the optical, NEOSurveyor observes in the infrared, and you want that if you really want to break the degeneracy between kind of like size and albedo of the objects. If you want to be really precise about it, let's put it that way, because with the optical we can actually get pretty far. And your third question was satellites. And usually the way this is phrased is, how much do you worry about Starlink? And the answer is, I think Starlink will not affect us materially. When it started, it was an issue. Their first generation, really first satellites that they put up there were really, really bright. And this kind of goes back to the question of, like what happens when things like that happen. People, especially engineers, tend to want to do the right thing. Sometimes you just don't know that they're hurting something else when they're doing their thing. So we reached out to SpaceX, had a lot of useful discussions about them. What are the issues, what are the problems, what are the pros and cons, how it can be mitigated. They figured out a way how to paint their satellites differently and figured out a way how to orient them differently so that they don't reflect light right at the time when they reflect light maximally. And now, if there is going to be an impact, it's going to be at percent to sub-percent level in terms of like pixels lost. And then we discovered on our end that we can, a lot of that we can fix in software. If there's a faint trail going over, we can figure out a way how to subtract it in software. So I think we're going to be fine when it comes to Starlink. Now, if there's this other company called Blue Ghost, there are these folks who put up like basketball-sized mirrors, effectively. There's only 3 or 4 of them up there, and they put up 10,000. I may be telling you a different thing, But I think their constellation is not built to grow to that level. Starlink is really the one that, and Kuiper to a degree, is the one that will have thousands of satellites, and for Rubin, that would be fine. I think the entire astronomy, sorry, I've thought about this for too much. The entire astronomy, I think our first reaction was shock, because it used to be that we didn't have to share the sky. It was ours. No one was up there. Oh, occasionally someone was up there, they would be, but now people have really started moving in, and now we're realizing that we have to learn how to share the sky, because these things are societally very useful and helpful, and to us as well. I collaborate with someone in rural Vermont. We talk to each other on Zoom every couple of days, and I can't even tell that he's like in the middle of nowhere on Starlink. So in exchange for a few pixels here and there that we lose, I think it's societally it seems like a good deal, and we have precedent for that, which is radio astronomy. So I'm not ever going to complain about Starlink. Every time I think about doing that, I look at my radio astronomy colleagues, and they have it much worse than anything we might ever have.
But we're working with Starlink as well. They've been very great to work with. Some of the other companies, not so much yet. So we'll see. All right. Thank you very much.